Can we start? Can we start the session? Is everyone there?
Yeah, hello, you can start.
Okay, right. Good evening, everyone. This is Blesson Mathew from Christ University. So we have 4 speakers for this session. So we should be finishing this session before 6:30. So I request all the speakers to maintain the time, and I'll be giving alert a few minutes before the time is up. So the first speaker is Snehalata Sahu. She will be talking about AstroSat UVIT legacy survey of globular clusters. Snehalata, you have 30 minutes.
Okay.
So you probably can wind up in 25 minutes so that we can have some questions reserved, right? Thank you.
Okay, thank you, Blesson. So first of all, I would like to thank the organizers for inviting me. And I also congratulate all the organizers and volunteers for putting such a hard work and making this event successful post-pandemic. So today I'm going to talk about AstroSat UVIT legacy survey of globular clusters. So this is coming from the ultraviolet imaging telescope observations from onboard Indian multi-wavelength spacecraft AstroSat. So most of the results which I'll be presenting today were done during my tenure at IIA and TIFR. So what are globular clusters? So they consist of thousands and millions of stars that are tightly bound by gravity. So you can see one image here, optical image of globular cluster. So they are spherically distributed around the center of the galaxy. They are mostly in the halo, and they are very old system. Like their ages range from 10 to 13 giga-year. Now, if you take all these stars and observe them and plot it in color magnitude diagram, this is luminosity and temperature. What you will note that they form a pattern like this, which is where most of the main sequence stars, they are distributed here. So they are burning hydrogen in their core. So most of the stars in the globular cluster, they lie in the main sequence. And then we have other advanced stages of evolution, like the stars red giant branch and horizontal branch, which have finished their hydrogen burning and they are evolving towards other advanced stages. And also we have some blue stragglers and horizontal branch and white dwarfs. So my main focus and the results that we'll be presenting will be based on these stars. So why? Because since we are interested in the UV observations, and these stars are very hot and their peak emission lies in the UV. So previously in the globular cluster, they were actually considered as single stellar populations. That is, all the stars in the cluster, they are formed from single age and metallicity. So this was a classical view. But with the recent observations from HST, very precise and high resolution observations, what they have found is that you see splits in various sequences. That is, in main sequence also you see the splits in red giant branch. Also you see extended horizontal branch. So what can be the reason for these splits? So these are the most of the studies nowadays are focused on this. Like, what is the reason that we see the splits? So thus, from these notion from the color magnitude diagram, so it is known now that all the globular cluster, they host multiple stellar populations. Now the reason why these splits are there, it is still not known properly, and many observational studies as well as theoretical are going on to understand this nature. Now focusing on the hot stars, horizontal branch stars. So they are mostly low mass stars that burn helium in their core, and they are of about mass like 0.5 solar mass and hydrogen in a cell. So based on their cell like hydrogen, like how much thick their cell is, they are distributed in the color magnitude diagram, and they populate mostly a roughly horizontal region. Like those with very thick cell, they will populate and they are known as red horizontal branch, and those thin cell, they will populate the more hotter side of the horizontal branch. Now coming, what is interesting is that from the HST and other observations, UV, it was found that there are some hot HV stars with temperatures greater than 20,000 Kelvin, like which have very thin cell or uh, uh, very less compared to their core helium, which is around 0.5 solar mass. So what is the reason for the formation of these extreme HV and blue hook stars? Is it like these stars have gone lot of mass loss in the red giant branch, or is there any other mechanism which is responsible for these stars? So this is also not understood properly. Now coming to why they are like important to study in UV. So when we know about elliptical galaxies which host mostly the old stellar populations. So this is the optical image and this is galaxy UV image. So what it was found is that though they are consist of old stellar populations, but also we see a UV emission. And when we plot the spectral energy distribution, we see a rise in far UV flux between 1800 to 2500 angstrom. So now the reason comes which stars are giving rise to this rise in flux. So one possibility could be these elliptical galaxies, they host these globular clusters. So the hot stars in this globular cluster might be causing this rise because their temperature profile is also similar to what we see in far UV. Now, another interesting fact about the globular clusters are there is that compared to the stellar neighborhood, these are the only system where all the physical process like stellar dynamics evolution, they take place in a time scale shorter than the Hubble time, which is 13 gigayears ago. And now stellar densities in these clusters, globular clusters, are also very high compared to our solar vicinity, that is around 1000 to 10 to the 6 stars per parsec cube. And mostly in the cores, they are very dense. So these high density, this can lead to dynamical interactions between the stars and produce some exotic objects which cannot be explained by normal standard stellar evolution. So these are one of the example is the blue straggler stars. So what are they? So these blue straggler stars, they were first discovered by Sandage in 1953 as a part of his PhD work. So here what you see is that the blue stragglers are brighter and bluer than these main sequence stars, and they lie above the main sequence turn-off of the globular cluster CMD. Now coming to this CMD, what you notice is that you see a turn-off like all the stars of around 0.8 of mass greater than 0.8 solar mass should have evolved long ago. But what we notice is that there are still some stars which lie above the main sequence turn-off. Now what puzzles the scientist is that how can these stars exist in these old environments, which look like young stars. So this is the globular cluster. Now you can also notice one thing is that their population is very less compared to other stars. So thus finding them is not an easy task. So now coming to why they are interesting to study, after discovering them through observationally in the CMD, what are the formation mechanisms that were proposed by the scientists? So the first thing is that either they could be formed from mass transfer, we need such a mechanism where the star would have gained some mass in order to make itself look younger and bluer. So these stars, they would have, for example, they would have transferred mass. Suppose a red giant star here, more evolved companion. So the main sequence would have sucked mass from this red giant star, and this would have evolved to a blue straggler, whereas this red giant would have evolved to the white dwarf. And similarly, there is also a lot of in the high density environment in the course of globular clusters, there are stellar collisions. So these collisions can lead to mergers and give rise to these massive blue straggler stars. Another mechanism which is proposed was this triple system. So there are a lot of primordial binaries existing in the clusters, and these binaries, they can undergo exchange interactions with another star, and thus this outer binary, it can cause this inner binary to lose energy and merge together, and thus lead to a massive blue straggler star. Now, depending on the environment of the clusters, So it depends how the blue stragglers are formed in each environment. So we need to study different type of clusters to understand their formation. Now you will ask why we want to study them, like what it will help us, like what it will help us in understanding. So the main thing is that these stars, they carry these dynamical signatures happening in globular clusters. So if we study these stars, since they are formed from a combination of stellar evolution and dynamics, they will help us in understanding their interplay and how different dynamical environment are causing different varieties of blue stragglers in globular clusters. So why it is difficult to observe them? So now from the ground-based telescope, if we look at the stars, since many of the stars, they are mostly these main sequence stars, old stars consist of. So it is difficult to observe them from ground telescope. So the reason is that if you see this SED, so most of the their energy, it peaks in the UV side, like the blue stragglers, compared to the other main sequence stars, which have temperatures like similar to sun or less than that. So so it is like you want to try to distinguish the fireflies when you have a huge light bulb in your front. So if you want to count the fireflies properly, that is the blue stragglers, you have to switch off this light bulb. So this can be done if you switch to UV. Switching means we are like just going to those spectral energy range where their peak emission lies. So thus, from the UVIT observations recently, this has been achieved in both open and globular clusters. So one of the example which I'll be discussing is we have detected white dwarf companion to a blue straggler using the UV data. Now, how the UV and optical CMDs look like. So this is the optical image and this is the UV image of the same cluster. Now you can see that most of the old stars and low mass stars, they cannot be seen here. Only the hot stars you can see, and the crowding is very less in the UV. So you are all familiar with the optical CMD. Now what happens when you switch to ultraviolet color magnitude diagram? So you can see here that these RGB and main sequence stars, their emission goes down in the UV CMD, whereas the hot stars HB and blue straggler, they are more prominently seen here, and they span more magnitude range. So thus UV, the ultraviolet plane, is ideal to study the photometric properties and population of blue straggler and HB stars. So this is one example of M3 cluster. So these are the blue stragglers and horizontal branch stars. So now coming to the background, why we were interested in conducting this survey. So from the previous observation, we have seen that these far UV CMDs, they are extremely powerful to probe the nature of these exotic objects such as blue straggler star. So one example is shown in 47 Tuc. So this is with UV observations and this is with optical. So we can clearly see that the blue stragglers, which are around 7,500 Kelvin here, it shows an UV excess, and that can only be explained by a white dwarf. So like that, we also discovered it by using the ultraviolet imaging telescope observations in globular cluster NGC 5466. So thus, only 2 blue straggler white dwarf systems are known so far in globular clusters. So now FUV-optical CMDs, they are extremely useful in understanding the horizontal branch discontinuities and also characterizing these multiple stellar populations in the clusters. One example is in case of NGC 1851. And also for deriving the complete senses of the luminous and post-HB stars that evolved from the horizontal branch stars. So this is also with UVIT we have discovered in NGC 2808 and also derived their properties. And also identifying this extremely faint EHB and blue hook stars, which are faint in optical, but they have peak emission in the UV. So one example is this UVIT observations of NGC 1851. So using also these UV observations, we detected a hot companion EHB to a blue straggler star. So thus these studies, this motivated us to do our legacy survey. Like we want to extend these studies to a large number of clusters and see how the properties vary in different types of clusters. So what was the main plan? So we had the HST observations in the central region, and this is the UVIT coverage, which is around 28 arc-minute field of view on top of the galaxy image zone. So what we did, we observed with UVIT and used HST because we need to build the color magnitude diagram ranging from optical to the UV to the optical. So we used other HST and these Gaia observations first to identify their membership, like whether they are all the members of the cluster, that is, they are all co-moving together along with the cluster members. And also, we also used this data to construct the UV optical CMDs. So the UVIT advantage is that its resolution is far better compared to GALEX. However, HST has much better resolution, whereas HST field of view is very less, if you see here, compared to the UVIT, like we can cover more region in the outskirts also. So thus we used all these data sets to make a complete full, like one of the example you can see here, this is the HST, the crowding is too much and it is resolved by HST. However, when we go to far UV, the crowding is less and also it covers more region by UVIT data of the same cluster. So the main, our motivation was to identify the FUV members covering the entire cluster region and also construct the FUV optical CMDs and provide this catalog for the future community, because these interesting targets, they can be used for the future spectroscopic observations in FUV. So the team led by Annapurni Subramaniam, so the director of IIA, and we also have other members from Italy and America, the other team members who have helped in this survey. So the first, there are three works which we are doing. So first is FUV optical color magnitude diagrams of 8 clusters. So this is submitted to MNRS and we have got positive comments and very minor corrections. So another study is evolutionary status of hot stars in M3 and M13 using this catalog data. And another is Omega Centauri in far UV. So this is being done by Deepthi, and she has also a poster. You can go through her poster and ask her if you want to know more about Omega Centauri in far UV. So mostly I'll be discussing about the first part of the results. We have 26 globular cluster proposed for observations in far UV filters with UVIT. So the distribution in galactic plane is shown here. So mostly we observed in 2 UVIT filters, the shown in blue and red. So we used 2 filters because we also need it for constructing the spectral energy distribution. And we had exposures varying from 4 kilosecond to 13 kiloseconds. So the main aim was to present the FUV catalog, as I said, and identify the evolutionary sequences of the hot stars, study the HB morphology, and also compare how it varies in different types of clusters, and derive the SED parameters of blue straggler and white dwarfs, and also identify if there is any UV excess in the FUV blue stragglers. So these are some of the UVIT images. So we can notice that except very massive and dense cluster, these are mostly resolved in other clusters in FUV by UVIT. So we combine this UVIT data with HST and Gaia DR3, as I said, but this is also not easy, like the cross match, because one example is so near. This is the UVIT, the left side is the UVIT image, and this is the HST near UV image in F275 filter. So you can notice there are a lot of stars in the same region. So however, if you take all these stars and plot it in the CMD, what you will notice that most of them lie here in the main sequence. However, only one hot star you will see that lies in blue straggler or in other region. So as I showed here, so if we give a cut in the color magnitude diagram and only select the hot stars in case of the HST, then it becomes more clear that we are on the same footing, that we are doing a right cross match. So this is for HST because HST resolution is 10 times better than UVIT. However, in the so this is the FUV optical CMD of this same cluster. So where we have identified these stars from in the inner region. And now for the outer region, we use the Gaia DR3 data with membership greater than 70%. And the cross, because they have similar this resolution, the cross matching was fine with the Gaia DR3 data. So this is the FUV-optical CMD. So after we identified all the stars from the photometry, so we constructed the FUV-optical CMD and also classified them, the blue stragglers, HB and white dwarfs. So we used several models to make sure that the classification is fine. So this is the horizontal branch models. So this is the extension of 0H main sequence because we expect the blue stragglers to lie in that extended part. There are no as such like proper models in photometry to use for blue stragglers. And these are the white dwarfs. So we see that we have identified all the hot stars nicely with proper motion membership. And so total we have around 1400 targets and 1700 from UVIT HST. So total sources is around 3000 in UV. We have 46 post HBs, 107 white dwarfs, 221 blue stragglers, and around 2800 HBs. So the highest that the largest population of PHBs and HBs is in the massive cluster M13, which is resolved by UVIT, and white dwarfs is in NGC 362. So this is what we did after obtaining the CMD. We stacked it so that the sequences are more prominent after correcting for reddening and distant modulus. So we can see that nicely that the horizontal branch stars are more clear now, and we have large number of white dwarfs and also some post HB stars and blue stragglers. Now, as compared to the GlobULeS previous studies, same stacked CMD, you can notice that since that time proper motion membership was not available, you have lot of background contaminants and it is not much clear, the sequences. Thus, UVIT has helped in achieving this. Now, what science work we can do now once we have this catalog? So this, if you see the spectral energy distribution of different helium abundances, so what you notice is that in horizontal branch, FUV is the most sensitive and UVIT filters span this range. So using this FUV and optical combination, we can infer the helium abundance variations and study them using the models. So one such what we did, we took this extension because this is what is sensitive to the helium for different clusters and plotted them with respect to the helium abundances that is been known from earlier studies. So what we notice is that this FUV optical extension, this is sensitive to the helium abundance variations and it is very strongly correlated, thus suggesting that FUV is the most suitable plane to study this. Now using these data, what science we can do? One example is, these two clusters M3 and M13, they have all similar properties, same age, metallicity, but you notice that their horizontal morphology is very different, which can be seen here. So what we did, we generated the models of different helium abundance to check like whether is it due to different helium, these variations are coming. So what we notice is that for M3, we can explain it with single initial helium abundance, whereas for M13, we need a helium enhancement of around 0.3 to explain this extended HPs. So this is done by Ranjan et al. So thus, these catalogs can be used for doing the science studies, and these are forthcoming, coming in the future, these studies. And another important thing what we can do, we can also plot the spectral energy distribution, as I said, and identify the UV excess blue stragglers and white dwarfs and derive their properties.
Excuse me, can you finish in 5 minutes?
Yeah, it is done. So thus, so for the first time, we are presenting the first results of 8 globular cluster from the AstroSat UVIT Legacy Survey Program. And we have detected around 3000 hot stellar sources from UVIT. And also we have shown one science case that this FUV is the most sensitive to the helium abundance variations, and they can be used for studying the using the models. Yeah, thank you.
Excellent. Thanks for keeping the time. Any questions? If any offline direct questions are there, can someone help me? I cannot see any questions in chat. Okay, can any volunteer help me to see whether they are having any questions directly?
Hello.
Yeah, hello. I can hear.
Yep.
Yeah, we have few questions.
Yeah.
Yeah, Snehalata, nice talk. So you have shown the blue sticker, and if you see the position in the chart diagram, I see many other stars at their position. So how you segregate this blue sticker from the other stars, which I think these are the field stars. If you the very first few slides, you will find that the same position there are other stars also. Right?
Okay, so you are asking how did we classify them, these blue stragglers?
Because at the same question, you have other stars which you are not classified as blue sticker.
Yeah, correct. So actually, I'll just show it. So if you can see this simultaneously, the color magnitude diagram. So this is NUV and this is in 336W band and this is in Gaia band and this is in FUV-optical. So we used all these three combinations because suppose if you have a blue straggler, you expect it to lie here and also here in the FUV-optical, and in the Gaia, you will expect it to lie above main sequence star. So we simultaneously checked whether they lie in all these regions and then classified them. And also what you notice is that this is just a photometric classification for now. And also we will derive the basic parameters from the spectral energy distribution, which will make it more clear because they have a certain temperature range and mass compared to the other hot stars. So we will use that. Now only we are photometrically classifying using all this spanning from FUV to optical, all the CMDs. Yeah.
So if you see this HR diagram, I understand all you have plotted only the members of the cluster, right? So what are the other stars? So the star.
You are talking about these stars? Hello?
Yeah, I also cannot hear.
Okay, so I can just say that these stars, they are not that much like bright or like they don't have that peak UV emission. So they will not be detected as you can see here. Only the hot stars we will detect in the far UV. Like we just randomly selected this region that are bluer than this and cross-matched, and you can directly notice that they follow this pattern. Like some of the HP stars, they lie in the expected location from the models, like that white dwarf and blue stragglers.
Okay, next question, we can have one or two more quick questions. I have a question.
Yeah.
Is this white dwarf population which you identified, are they new or was it studied earlier?
No, they are not new, but they are also not studied. Like the properties are not determined in different clusters.
Yeah.
They are just also their membership is not known properly, but we can see a sequence and we are just showing that in HST.
Right.
So what is our interest is that we want to derive their properties and see in different cluster, like what is their average mass, like are they 0.5 solar mass, which is expected in globular clusters, or it is less than that. Because we have also found one interesting study in case of M3, M13, where the white dwarfs, okay, this one, I am not showing here, but the white dwarfs of M3 and M13, like the average masses are different. Like for M3, they are more massive, the white dwarfs, compared to the M13, which have around 0.3 to 0.4 solar mass.
So you are yet to characterize these white dwarfs in a proper way, like what type it is and all.
Yeah, that is done in this study, and we'll be reporting that in a
Right. Thanks. Any more questions? One
Yeah,
final
this
question.
is just a quick question. You have this UVIT observation of corona part, not the core part, because for the core part you have taken the HST observation. Right? For the surrounding part you taken UV, but UVIT is also the central portion, right? have you compared this HST versus UV in the central part? What is the fraction we are getting in the UV?
Yeah. Like for like these clusters we can't use because this is not result in UVIT, but like for M13, M3, we can compare with HST, and what we have found is that all the HB stars that are detected in HB or other hot stars that are detected in HST, we also detect those on in UVIT. Like it is not like we are losing anything. Like whatever stars we see here, which are located in the central region, we also found in FUV, and also for blue stragglers and white dwarfs. Like, but we can't talk about other stars because if you look at NUV image of HST, you will also have these stars because they emit there in NUV, and the depth is also more, the magnitude depth. However, FUV we only find this HB and BSS stars, and depth it can go is around 22 to 23 magnitude.
Okay.
I think time is up. So thanks, Snehalata. But
Yeah,
there is this
thank
one
you.
question in the chat box. You can possibly answer. Okay.
Yeah.
That question is by Manas. Manas asking, like, can one apply single evolutionary model to study all population of globular clusters, including white dwarfs? Okay, you may reply to that in the chat box. Okay.
Okay, I'll reply that. Okay, thank you.
Right. Let's go to next speaker. Next speaker is Kaushar. Yeah, Kaushar is there.
Yes.
Okay, you have 15 minutes. Please go ahead.
Thank you, Blesson. First of all, I would like to express my gratitude for this wonderful opportunity to present our work. I am Kaushar Vaidya from Department of Physics, BITS Pilani. And today I'll be presenting the blue straggler populations of open cluster NGC 7789 with UVIT on behalf of my collaborators, which are Anju Panthi, Manan Agrawal, Sindhu Pandey, Khushbu Rao, Vikrant Jadhav, and Annapurni Subramaniam. So this work was published in MNRS a month ago. Since the previous speaker, Snehalata, has done an excellent job of explaining the blue straggler stars, I'll go quickly through the introduction and the description of formation channels. I'll describe the cluster and then tell which data set we have used. I'll discuss the procedure that we used for the spectral energy distributions fitting of the BSS, and then I'll describe our main results. So in the times when human beings are very fascinated with everything anti-aging, it's really fun to study these stars which have cracked this. So blue straggler stars are exotic stars and do not seem to follow the standard theory of single star evolution. They were discovered 70 years back in globular cluster, and they are now found in every kind of stellar environments. Here is an example of a color magnitude diagram of an open cluster, M67. This is taken from Liner et al. Here, all the members determined based on the WIN open cluster survey are plotted. So basically, this is the location of blue stragglers along the extension of the main sequence. And that's why classically they are defined as brighter and bluer than turn-off. Because they are all members, the only reason why they can linger on to the main sequence is because they may have rejuvenated, and that can happen when the progenitors of BSS gain mass and therefore also some extra hydrogen fuel to continue on the main sequence. So how do the BSS progenitors gain mass and rejuvenate? There are three main theories: stellar collisions, mass transfer, and merger of an inner binary. The direct collision between single stars, or the collisions between binaries with single stars, or binaries among themselves in dynamical interactions, can give rise to the formation of BSS. However, this mechanism is feasible in dense environments such as the globular clusters or cores of the open clusters. Mass transfer itself can be subdivided into 3 categories depending upon the evolutionary stage of the primary at the time of mass transfer. So there is case A when both primary and secondary are on main sequence. So here we are talking about a tight binary which due to losing angular momentum go on to merger, and we have a single BSS, or we may have a binary BSS with a short period main sequence companion. The other 2 cases are the examples of Roche-Loeb overflow mass transfer. There we have case B when the primary is on RGB. So here the resultant is a short period binary with a helium white dwarf of mass less than 0.45 solar mass as a companion. And in case C, we have the primary is on AGV. And this process gives rise to a longer period binary with a carbon oxygen white dwarf as a companion. And there's a third possibility where there is a hierarchical triple system, and the BSS is a part of inner binary. It gains mass from the primary, which then evolves to another component. So this here also BSS can either form through mass transfer or merger. So our objective is we want to understand the formation mechanisms that are dominant in different environments. We have been studying blue stragglers of open clusters. And what facilitates these studies is one, the precise astrometry that is available from Gaia, and two, the UVIT observations which help us to characterize the BSS, as well as detect if there are any hot companions and thus constrain the formation mechanisms. So this cluster is an intermediate age cluster. It's about 1.6 gigayear and its distance is about 2 kiloparsec. Its metallicity is 0.02 plus or minus 0.04. And the cluster members were recently presented by 9 et al. They had a WIN open cluster survey through which they found radial velocity plus Gaia DR2 proper motion members. They found 624 members which extend about 1 magnitude below the turnoff. They also found 81 single line and double line spectroscopic binaries, and they identified 12 BSS. In our previous work, we studied 11 open clusters, blue straggler stars, to basically know the dynamical ages or the use of BSS as dynamical age prediction. So in that, we also studied this cluster, and we identified the members using Gaia DR2 proper motions. So we found 4 additional BSS than what were reported by 9 et al. So here in this work, we are focusing on all of these 16 BSS candidates. So the UVIT observed this cluster in July 2017. So we have NUV observations in 3 filters, as well as the FUV observation in F169M. And to do the data analysis, we followed the standard steps. We used CCD Lab to produce science study images. We used IRAF for point spread function photometry. And these are the PSFs and number of detections in individual filters. And we obtained the UV magnitudes in the AB system by using the 0-point magnitudes in Tandon et al. And applied the aperture and saturation corrections. We cross-correlated the UVIT detections with the Gaia members as well as the 9 et al. Members. So here are the members which are having a counterpart in the FUV and NUV. So now I'll show a color magnitude diagram of N245M detections which are having Gaia or 9 et al. Membership. So here all of the sources are having N245M detections, but the green ones are the ones which are members according to Rao et al. And the red ones are the members according to 9 et al. The BSS are seen over here. We have used different symbols. Some of the BSS are known to be binaries, single line spectroscopic binaries, 4 of them, which are shown in yellow open circles. 8 of them are single members, which are shown as blue open circles. And these 4 dots are basically Rawatal members, which are not there in 9-atal. So they are not members either because they are rapid rotators or because their radial velocities are not available. So going ahead, let me explain how we constructed the spectral energy distributions. We used a virtual observatory SED analyzer, or VOSA in short. And VOSA actually performs these 4 operations. It first compiles the photometry based on the coordinates that we provide. It then corrects for the extinction based on the value of extinction that we give and the extinction laws that are available. And then it calculates the synthetic photometry in all the filters that we want to fit the SED. And finally, it suggests us the best 5 or 10 models based on the minimization of reduced chi-squared, which is calculated as per this expression. So we used approximately 13 to 20 photometric data points, which range from FUV to mid-IR. We, of course, used the AstroSat FUV and NUV, but in addition, we also had GlobULeS data for NUV. For optical, we used Gaia EDR3 and PanSTARRS, as well as the original first photometric survey by G. Mattel. And for IR, we used 2MAS and WISE. We provided this value for extinction correction, which we had estimated from the Gaia DR2 members. And we used Kuruk's stellar models. So we kept the temperature and log G as the free parameters. Temperature ranges from 5,000 to 50,000 Kelvin. Log G value ranges from 3 to 5. And we fixed the metallicity to 0 because that is closest to the known metallicity 0.02 plus or minus 0.04. So here is an example of one SED where we can see on the y-axis, we have flux plotted against the x-axis, which is the wavelength. All the observed data points after the extinction corrected are shown in the red points. And the green curve is basically the synthetic photometry calculated by VOSA. As can be seen, the errors, photometric errors are very small. Therefore, the error bars are not visible, except here where it's a WISE data point and it has a large error. In some of the cases, the WISE W4 filters only have upper limits and not really the fluxes. So those are not included in the fitting. In the lower panel, we see fractional residual, which is basically the ratio of the difference in the observed and model flux divided by the model flux. And we can see that the fractional residual is nearly 0 in this case. So what do we learn from these SEDs that we fitted on these 15 BSS? We could not fit one because it had a nearby source, but we fitted 15 BSS. So what did we learn? First of all, we found that in 8 of the BSS, there is no excess in the UV filter. So they are successfully fitted with a single temperature SED. We characterize the parameters of BSS by these SEDs. We found 2 BSS which have excess in the UV flux, which is greater than 30% or fractional residual 0.3, but we could not find a good fit using the 2 component SEDs. So these are not attempted here. And we found 5 BSS having excess flux, and they were successfully fitted with the 2 component SEDs. So let me share how we fitted the 2 component SEDs now. We use this pipeline called binary SED fitting, available on GitHub by Jadhav et al. And we use the Kaushar model to fit the hot component. In the Kaushar model, the temperature can range from 5,000 to 80,000, and log G will range from 6.5 to 9.5. So let me show an example of one more point. We estimated the errors in the parameters of the hot components using the statistical approach. If there is a time available or if there are questions, I'll detail this. All right, so here is an example of a 2-component BSS where we can see that the UV data points, including the GlobULeS, no, I'm sorry, there's no GlobULeS here. So all the UV data points have excess, but the maximum excess is in the FUV.
Excuse me, 2 more minutes.
Yeah, sure. So here we can see that the fractional residual goes to 0 in the composite curve, which is green, as compared to the single one which is yellow. So here are the parameters of the hot components and the BSS. So as we can see, the temperatures range from 11,750 Kelvin to approximately 15,500. And these are the radii. As you can see, some of them are like white dwarfs. But in order to know what are they, we plotted an HR diagram on which we plotted the previously identified hot companions of different clusters, for example, NGC 188, 1851, King 2, as well as the 7789 BSS. So here are the 7789 BSS. These are the single ones. And the open squares are the two component ones, and their hot companions are over here. So the solid as well as the dash curves here are the low mass or extremely low mass white dwarf curves from Panay et al. And Althaus et al. So they range from mass 0.15 to 0.24. We can see that the hot companions are all near 0.17 or 0.18 solar mass ELM white dwarf curves. So we find that all of them are likely extremely low mass white dwarfs. So what do we infer from this? First of all, since extremely low mass white dwarfs cannot form from a single star in a Hubble time, therefore this confirms the formation mechanism as the mass transfer for these BSS. However, we have two BSS which are known single line spectroscopic binaries with large orbital periods. So therefore, these periods are inconsistent with the case A, case B mechanism. And what we contemplate is that perhaps these BSS are the inner binary of hierarchical triple systems, and they have obtained mass from the primary, which then evolved to ELM white dwarf. And this inner binary is yet to be characterized. So I come to the conclusions now. We basically characterized 16 BSS of open cluster 7789 using UVIT data. Out of 15, 8 were successfully fitted with a single component SEDs. We discovered 5 likely ELM white dwarfs of masses less than 0.18 solar mass and temperatures ranging from 11,750 to 15,500 as hot companions in 5 BSS. And the two known SB1 could be inner binary of the triple systems with the detected ELM white dwarf in a yet to be identified close orbit. There are 2 more BSS that show excess, but we cannot successfully fit a second component. So therefore, we conclude that at least 5 of the 15 or 33% have formed via the mass transfer. Thank you very much.
Thank you, Kaushar. Any questions? I have this quick question. I mean, you are keeping this temperature and log GS3 parameters, right?
Hello, we have a question here.
Can I finish my question?
Yes, please. Yes.
Yeah. So instead of keeping both as free parameters, have you tried fixing one and keeping the other one? Because why am I asking this question is when we looked into the hot stars and all, we found that the routine can, let's say, the VOSA can give you different combinations, right? So when we keep 2 parameters as free parameters, it's a bit risky. But if we can lock one parameter through some means, for example, from spectrum, we used to do that for fixing the temperature. Is there a way in the case of blue stragglers?
I see. No, we haven't tried that. Maybe in the very initial stage we did, but in the final analysis we did not try. I'll look into it. Yeah. Thank you for your feedback.
Thank you. Yes, question, please.
Yes.
Hello. So I had one is a quick question because you used W4, which and even 2 mass. The beams are very large, right? Like W4 is like 12 arcs.
Right.
If you consider UVIT, that's very small HST. So how did you eliminate it? Because there could be other sources contributing to this. One question. The second one, what do you infer about the blue stragglers which do not have companions? Because this is an open cluster. So what do you infer? Is it collisional or is it binary or with the main sequence companion? Because the probability of that occurring in an open cluster is very low.
Right.
I've thought.
Yeah, so for the first question, actually, W4 was not included in any of the fits because those were all upper limits. As a check, we actually went to Gaia or to Mars, and we checked if there were any nearby sources within like 2 arcsecond or 3 arcsecond. We discarded one BSS simply because there was one in 3 arcseconds. So that is the check that we have done. Since there were no like Spitzer or higher resolution options available, this is what we had. But nevertheless, W4 was still not included. It was just shown as an upper limit. So that is the first question's response. The second is, what do we learn about the BSS which are fitted successfully with a single? We haven't really looked into the details whether or not collision can explain that. But however, we know from the previous other works that collision is extremely less likely in an open cluster. So one possibility, for example, there are 2 more SB1s for which we could not find a 2 component. So maybe the possibility is that it is a cooler component which could not be detected in UV because of no excess. Maybe that could be one possibility, because we have 2 SB1s for which we could not find the component.
So you would not rule out mass transfer, because even in that case, it would be a mass transfer.
Right. Yeah. Thank you.
Yeah.
Any other questions? Yeah. Thank you. Okay. Saurav, you have a question? Okay, checking the chat. Okay, I think Manash has the same question which Sarita asked. Saurav, would you please type your in the chat box? Manash, your question was the same as Sarita's, so I think that is answered. Saurav, the RV measurements are available for all the BSS in 9 at all. It was published in 2020. Right, but there are some young open clusters which do have 10 to 12 BSS, including 7, 7, 8, 9 years. 1.6 gigayear. Yeah. So I suspect that maybe those could be called cooler companions, which were not detected as extra UV flux. The Blesson is writing is not able to unmute. Can you look into it?
Okay. Right. Thanks, Kaushar. Yeah. So shall we go to the next speaker? Hello.
Yeah, hello.
Okay, next speaker is Chirag. Okay, you may go ahead. Yeah.
So, good evening. Good evening, everyone. I'm Chirag from TIFR Bombay. So today I'll be discussing about how, with the help of Gaia, we would be able to detect hundreds of black holes in the Milky Way galaxy. So, although we know that single-slit evolution is largely understood, still we have some uncertainties in understanding the evolution of the high mass stars. I mean, how they evolve and then go through supernova and create the remnant. And in particular, we do not clearly understand how to connect the evolution of high mass stars to the progenitor properties, maybe the pre-collapse progenitor and the ZMS progenitor. And theories are not mature enough in order to provide constraint from the first principle and without the need of the observations. So, and also the high mass stars are few in number, and it is hard to infer the connection of the black hole properties from, and the progenitor properties with the observations like X-ray and radio and from the currently applied gravitational wave astronomy. However, understanding the connection between the black hole and its progenitor is important in order to understand many aspects of astrophysics, such as astrophysical implication and theoretical merger rates, which are calculated for the black hole mergers detected by LIGO, in order to understand the mechanism of gamma ray burst, and in order to understand the mechanism of supernova. So, in order to make significant progress, we need two things. We need many detections of these black hole binaries, and we need to be able to connect the properties of the black hole with the progenitor in a model independent way. So the idea is we have these luminous companion systems with a black hole, and black hole is unseen. So Gaia will be seeing the motion of the luminous star, as you can see in the animation. And if the properties of the luminous companion, such as the metallicity and age, are known, we can, and since the black hole progenitor was part of the binary, we can put some constraint on the black hole, and it will share the similar properties as the luminous star. So we have created a highly realistic PHLC population in the detached binary system, and we ask whether or not Gaia would be able to resolve such binaries. And we find in our studies that yes, Gaia would be able to detect hundreds of these systems, and with the properties of the luminous star, we can constrain the properties of the black hole progenitor. So we have used the binary population synthesis suite, that is COSMIC, in order to generate a realistic compact binary population in the Milky Way. And COSMIC uses BSE in order to involve initialized set of binaries based on the preferred star formation history and adopted evolution model. And it incorporates all the important binary interaction physics, such as metallicity dependent star evolution, wind prescription, supernova physics, and mass transfer and tides. So how do COSMIC generate compact binary population which contains a black hole with a luminous star? So first we initialize these binaries, giving them the initial ZAMS masses and metallicity. And we also provide initial orbital properties such as eccentricity and the orbital period. And likewise, we create our initial binary population. And by choosing the evolution model, we evolve these initialized set of binaries in which one of the star will go through a supernova and create a black hole, while another is a luminous star, whether main sequence or the post-main sequence. And that will give us our evolved binary population where we have a luminous star with a black hole. So for the initialized set of our binaries, we are sampling the primary masses from the Kripa mass distribution function. The mass ratio is assumed to be uniform in log, is uniform from 0 to 1, and we are selecting the lower limit on the secondary mass as to be 0.08 solar masses. We are assuming a log uniform semi-major axis, and initial eccentricity is assumed to be thermal. We are selecting 0.5 of the binary fraction. And for this study, we are using two widely used supernova mechanism to create black holes formation, mainly rapid and delayed. So with the rapid supernova prescription, we expect the lower mass gap between 3 to 5 solar mass. On the other hand, with the delayed mechanism, we expect a continuous compact object mass distribution. And as we know that the compact object during their formation imparts a kick from the explosion. And for that, we are sampling the kicks from the Maxwellian distribution, where the sigma is 265 kilometer per second, which is then scaled down based on the mass fallback onto the black hole. So for this study, we are assuming a metallicity dependent star formation history, which is based on the lattice suite of fire simulation 2, which preserves the complex correlation between the metallicity, age, and position of stars in the Milky Way. And likewise, preserving this age, metallicity, and galactic position correlation, we are distributing the evolved binary population in the Milky Way. And from the simulated set of present day binary population, we are performing 200 realization in order to incorporate the effects of the statistical fluctuation of the Gaia resolved binaries. And for a binary to be detectable by Gaia, it has to fulfill 3 constraints. So the orbital period should be less than 10 years, the Gaia G magnitude should be less than 20, and the sky projected angular size, which is denoted by alpha, should be greater than the single Gaia position error. And on top of it, if a binary has to have a confirmed black hole, we imply an extra condition where the uncertainty in the mass determination of the black hole should be such that the mass determination minus the uncertainty should be greater than 3 solar mass. So that we are confirmed that the heavier mass, which is not seen, is not a neutron star, and we are sure that it is a black hole. And to incorporate the effect of reddening, we are using a 3D dust map by Bowie et al. So for our results, first of all, I'm showing in this figure the orbital period distribution of these BHLC binaries in the Milky Way. And in this figure, the orange curve is showing all the luminous companion binaries with a black hole. The blue curve shows all the binaries which went through a common envelope during its evolution at least once. And the green curve shows all the binaries which never went through a common envelope. And as you can see, there is a clear bimodal distribution in the orbital period for these binaries, where the short period binaries are predominantly coming from the common envelope evolution, whereas the binaries in the large orbit are coming from no common envelope. And the vertical line shows the first detectability cut, that is on the orbital period, should be less than 10 years. So as you can see, Gaia will be sensitive to both binaries coming from the common envelope and the non-common envelope. After this slide, I'll be discussing the result based on the Gaia resolvability conditions. So this is the color scheme. The red denotes all the black hole binaries with the main sequence companion. The blue denotes all the binaries with the post main sequence companion, and the purple denotes all the BHLC binaries. So for the astrometric cuts, we are choosing 2 constraints. So for the optimistic, alpha has to be greater than the Gaia's position error, and for the pessimistic, alpha has to be greater than 3 times the Gaia position error. And as you can see, our models predict that about 300 of these binaries would be detectable in rapid, and around 100 of them would be detectable through delayed. And the number of binaries are smaller in case of delayed as a result of more number of disruption due to higher natal kicks in the rapid supernova model in comparison to delayed in the delayed supernova model in comparison to rapid supernova model. And as we have discussed the confirmed black hole candidates for these systems, so in our Gaia resolved population, which shows that 1/3 of the Gaia resolved binaries would have confirmed black hole candidates, both in case of rapid and delayed, as you can see from the cumulative plots of these Gaia resolved confirmed black hole candidates. In the next figure, I'm showing the distribution of the Gaia resolved binaries in the 2D plane, where x-axis is the black hole mass and the y-axis is the metallicity. And for the first time, if these binaries would be detected, we would be able to comment on the black hole progenitor, and which separates these binaries from the ones detected through X-ray or the gravitation wave astronomy in a model independent way. And since our detection condition is purely based on the luminous companion properties, and as I'm showing in this figure, the detection fraction is uncorrelated with the black hole mass. So the selection biases, which are based on the black hole mass, are not present in the binaries detectable through these methods. So till now, I have discussed about how, with the help of astrometry only, we would be able to detect these binaries. And we have also searched for the RV follow-up. So in the current figure, I'm showing the cumulative plot for all the binaries which are resolved by Gaia. And I'm showing the radial velocity semi-amplitude for these binaries. And as you can see, about 20% of these binaries would, in case of both rapid and delayed, would be resolved by the Gaia radial velocity spectrometer itself. And some of our binaries in our data, which is resolved by Gaia, have X-ray counterparts. And with the help of Chandra X-ray Observatory and E Rosetta band, we find at least 1/3 of the Gaia resolved binaries would be sensitive to both Chandra and E Rosetta. So to summarize, for the detectable population in the Gaia, that it would have well-constrained progenitor properties, and since we have seen that the detectability does not strongly depend on the black hole mass, hence the detected mass distribution should be very close to the intrinsic distribution of the BHLC binaries in the Milky Way, and most of these binaries, most of the detached binaries are not detectable by gravitation waves or X-ray or the radio astronomy. Hence, this will create a complementary set. And we have also seen that the RV follow-ups using Gaia as well as other telescopes can improve the constraint on the black hole masses. And some of these binaries may have an X-ray counterpart. Thus, it will constrain the stellar winds as well as the accretion paradigm in the systems like these. So at last, I would just leave you with this figure where I'm showing all the resolved binaries in the blue color, and about 1/3 of these binaries would have a confirmed black hole candidates with the help of astrometry only, and the same fraction of binaries are have X-ray counterparts, and about 20% of these binaries would be resolved by Gaia RV spectrometer, and about 6% of the system will have constraint from astrometry, RV, as well as X-ray counterparts. Thank you.
Thank you. Any questions? Any quick questions? Since we are running late, we can have one quick question.
Yeah, we have a question.
Okay.
The ones which are likely, how did you estimate the ones which are likely to be visible in Chandra or Rosetta? Was it based on the evolutionary time scale? Or?
No. So what we have done.
Hello, am I audible?
Blesson, can you hear me? This is Abhay.
Yeah. Am I audible? Yeah.
Yeah, I can hear you.
Yeah. Right. So shall we go to next speaker? Next speaker is Abhay.
Yeah, so I'm just going to share the screen.
Okay. Okay.
So can you confirm? Is it visible?
Yeah. Go ahead. Yeah. Thanks.
Yeah. So I'm just trying to
You can
see
make
on
it
the
full screen. Yeah.
Full screen. Is it now full screen? Can you see it?
No.
Not yet. Okay.
Yeah. Is it PDF?
No, it's actually PowerPoint. So,
okay. Yeah. Done. Yeah. Go ahead.
Okay. So thank you, Blesson. First of all, I would like to thank ASI for giving me this opportunity to share my work based on B-type stars. This work which I'm going to present is done in collaboration with Mukesh Sahu, Arjit Mathew, Wolfgang Glassel, and Santosh Joshi. Now, if you look at the stars in general, so some of the stars, they show variation in their brightness profile. So for example, this data where on the x-axis we have time and on the y-axis we have magnitude of the star. So you can clearly see that this star is showing variation in its magnitude. This data is taken from test for one B-type star known as MWC137. So now, if we have variability in stars, so what this variability indicates actually? So obviously there must be a reason, there must be something which is causing this kind of variability. So apart from several mechanisms, pulsation was one of the underlying mechanism which was proposed, that these variabilities are due to pulsation in stars. So obviously, if we have a system and we see such kind of variability, then it indicates that some kind of instability is present in the system. And obviously, if we want to study the instability of a system, then we have to perform a stability analysis. In this case, we are considering stars. So we have to perform a stability analysis in models of stars. And then later on, we have to identify that what is the origin of these instabilities. So how this stability analysis in stars are performed, this is basically a two-step process. So in the first step, we construct model of stars. So these models are basically hydrostatic models. And in the second part, we perform perturbation, or we apply perturbation on these models. And then we'll see whether this perturbation grows with respect to time or it decays with respect to time. If the perturbation grows with respect to time, we say that our model is unstable, and then we perform non-numerical simulations to identify that what is the final consequence of instability. Now, so first, I will briefly discuss about the construction part of the models, so how we construct the models, and then later on, I will briefly mention that how we apply perturbation technique for doing a stability analysis. So now here, in order to construct the stellar models, we do some modification, some simplification, and this simplification actually help us to construct the models. So for example, we neglect magnetic fields and rotations. We know that magnetic fields and rotations are present, but just to simplify the situation, we neglect it. And then we assume spherical symmetry and we adopt Lagrangian description. Here we generally take mass and time as an independent coordinate. In some techniques, radius and time, they are taken as independent coordinates. So to construct the models, we generally rely on the conservation principle. So we take mass conservation, momentum conservation, energy conservation, and energy transport together with boundary conditions. So these four equations, I'm not going to describe the details of these equations. The intention is to show that these four fundamental equations are used to construct the model of stars. Just to highlight that here on the left hand side, we have radius, we have pressure indicated by P, we have luminosity indicated by L, and we have temperature indicated by T, and small m and T, they are the our independent variable. So small m is the mass and the small t is the time. Now we take these four equations and boundary conditions to construct our model of star. Now, obviously, we know that the stars at the core, the nuclear reactions are going on. But if we want to study the dynamical instability in our stars, so in most of the cases, the dynamical instabilities, they are present only in the outer part of the star. So what we can do, we can construct the envelope model of the stars rather than constructing the entire model of the star. So here, just a numerical scheme is given, just cartoon representation of numerical scheme is given here. So what we do, we just simplify the entire star in one grid. So this is one-dimensional model of our star. And here, this is representing the surface, and this area is representing the inner part of our stellar envelope. So here, beyond that, we are not considering. So this is the envelope region of our star. We take the boundary conditions such as effective temperature and the radius by using the Stephan-Boltzmann relation, and we use the effective pressure, and then we integrate towards the inner side of the star, means inner side of our models where temperature are increasing. So we can provide a cutoff at the temperature like 10 to the power 7 K to construct the envelope of our star. Now, these methods basically simplify our situation. So what we have hydrostatic and thermal equilibrium. We are neglecting the nuclear energy generation, and we are constructing a simplified model as an initial problem. Now, we have our models. So the second step was to perform the linear stability analysis to know whether model is stable or unstable. And how do we do that? We just take the general perturbation approach. So we apply small perturbation, and then we see whether perturbation grows with respect to time or it decays. So here, for example, let's say we have a quantity X which depends upon the mass and the time. This X can be anything, for example, temperature, pressure, or luminosity. So we apply a small perturbation. So here it is written X naught M and then X prime M on T. So this X naught M is representing the hydrostatic value, and X prime is representing basically the applied perturbation. So X prime is quite small compared to our hydrostatic value. Ultimately, we apply the separation of variables, and then we perform the linearization. So basically, we neglect all the higher order terms, only keeping the first order term, and then we get the so-called boundary value problem, where our eigenvalues are basically complex. So it means they will have a real part and the imaginary part. In the adopted normalization, what will happen that we'll see that the real part of our eigenvalue, they will tell us about the period, and the imaginary part of our eigenvalue will tell us whether the given mode is stable or unstable. Means particular mode is damped, or we have instability associated with that mode. And this boundary value problem can be solved by any standard numerical method. So for example, in our case, we have used the Riccati method. Now, so what will happen if we get the eigenfrequencies? So we construct a so-called very informative model diagram. So in this model diagram, what we have on the x-axis, we have stellar parameter. For example, these parameters can be like mass of our model or the effective temperature associated with our model. And on y-axis, we have eigenvalues. So these eigenvalue may be the real part of the eigenvalue or the imaginary part of our eigenvalue. So you see here, for each models, we have infinite set of eigenvalues. So for example, here, this is represented by 0.1, 0.2, and 0.3. These cross points are representing the eigenvalues for one model. And we have maybe for the next model, we again have several eigenvalues. And for the next model, we again have several eigenvalues and so on. So by plotting the eigenvalues as a function of stellar parameter, for example, mass or effective temperature, we get the so-called model diagram. Now, since we know that we have constructed now the model of the star, and now we are in a situation to perform the linear stability analysis to know whether model is stable or unstable, we can go to study the our special B type of stars. So for in the present today, I am going to just share these three cases. So in case one, I will talk about SD2905. It is also known as Kappa SOP. In case 2, I will talk about a PE type stars MWC137, and in case 3, I will briefly discuss the results of SD564. Now,
excuse me, you have 2 more minutes.
Okay, so now in case of B type stars, we have the surface temperature which is of the order of 10,000 to 30,000 Kelvin. So now you see here what is in our case 1, what we have the radial fundamental mode, which is over here. So on the x-axis we have mass, and on the y-axis we have our eigenfrequencies. In the left figure we have real part of our eigenvalue, and in the right side we have imaginary part of our eigenvalue. So here you see these two modes the first fundamental mode and the the first overtone, which is unstable for our star SD2905. If we convert the frequency into period, so you see that the models which are having mass 34 to 34.5 solar mass, they are representing the period which is around 2.7 days, which is the observed period of our star. So we can explain this variability in terms of radial pulsation in the case of 2905. Now, we also perform the nonlinear simulations, and in the case of nonlinear simulation, it also indicates that 2.7 days pulsation is basically the final fate of our unstable model. Now, in case of the another star, which is MW137, we perform the same technique, we perform the same analysis, where the observed pulsation period was 1.9 days. And you see here on the in this plot, this is again the period on the left on the y-axis, and we have model mass on the x-axis. So here this line, which is the dotted line, is representing the observed period. So our model, which has mass between somewhere around 45 solar mass, is representing this 1.9 days. So that's how this 1.9 days of period in one MWC137 can be explained by using the radial pulsation. Now we perform the nonlinear calculations, and the result is same. 1.9 days can be explained in terms of radial pulsation. So in case 3, which is for SD564, we performed the linear stability analysis, but no, the observed pulsation period was around 37 days, but we did not find any pulsation period in our models close to 37 days. So the model, which is the modes which are unstable in our considered mass range, they are having 12.5 days. So it means that models, they are very far from the actual period which has been observed. So obviously these models, I told you earlier that we have neglected rotation, we have neglected the magnetic field. So obviously in order to see the impact of those things, we have to improve our models. So we have to include the rotation, as well as, if possible, we have to include the magnetic effect of magnetic field. So in future, we are planning to perform analysis of B-type stars using the test data. Test data is very fine and accurate. We would like to use the test data, and particularly we'll be interested to model the stars where we have high lunar to mass ratio. So I'm not going into the detail. I'm just going to the summary because I have limited time. So just to take away the takeaway message here, I would like to mention that the variability of B-type stars can be understood up to certain extents by pulsation. And in case of these 3 B-type stars, whatever I have mentioned here, only for 2 we can explain the variability in terms of radial pulsation. But in case of SD564, the models were predicting 12.5 days, which was really not even close to the 37 days variability which was observed. So obviously, we have to improve our models. Ultimately, the instabilities which are present in our models, we also need to consider whether they will lead any kind of episodes of enhanced mass loss or not. I have not discussed in detail, but some of the models have shown that these instabilities can even initiate or can even ignite the surface eruptions in the models, in the considered models. So thank you very much.
Thank you, Abhay. If there are any questions, you can put in the chat box, because we don't have time for questions. Also, I have been informed from the main venue that they lost connection with us, which means Wi-Fi is not working there. So, anyway, we will go ahead with the next presentation. Once they set it up, that will be done, right? I mean, so, but then if you have any questions, you can put that in the chat box. Thanks, Abhay, again.
Okay, yeah.
Let's go for final speaker of the day, Sabyasachi. Yeah, you may go ahead with presentation.
Hello,
full screen.
am I audible?
Yeah, you're audible. Yes.
Okay. Good evening, everyone. I'm Sabyasachi Pal, and today I will speak about what we can learn from the recent outburst of XO2030 plus 375. Here is the plan of my talk. The X-ray pulsar XO2030 plus 375 was discovered by the AstroSat in 1985 May during a giant outburst using the AstroSat observation in 1985. The spin and orbital periods of the pulsar were estimated to be 42 seconds and 46 days respectively. The cyclotron resonance scattering feature for the source was doubtful. It is interesting to explore the source during the recent giant outburst in 2021. We have studied the evolution of the timing and spectral properties using different NuSTAR and NICER observation throughout the outburst. The critical luminosity is crucial to determine whether the radiation pressure of the emitting plasma is capable of decelerating the accretion flow. Critical luminosity is the luminosity above which a state transition from subcritical to supercritical take place. The subcritical state is known to be the low luminosity state, whereas the supercritical state is the high luminosity state. The luminosity of XO2030 plus 375 during the 2021 giant outburst was higher than the critical luminosity. So it is expected that a state transition from subcritical to supercritical regime took place. Here in this diagram, we have shown two different beaming patterns. In the supercritical regime, radiation pressure is high enough to stop the accretion matter at a distance above the neutron star, forming a radiation-dominated shock. X-rays are released in the shape of a fan beam from the sides of the accretion column in this scenario. For the subcritical regime, accretion material reaches the neutron star surface through nuclear collisions with atmospheric protons or through Coulomb collisions with thermal electrons. However, the beaming patterns can be more complex than a simple pencil or fan beam. We have used data from NICER and NuSTAR and studied different properties of XO2030 plus 375 during the 2021 outburst. We have followed the standard data reduction procedure as provided by the observatory. We have used most of the TO data from our proposals. The X-ray pulsar XO2030 plus 375 went through a giant outburst in July 2021, and the X-ray flux reached a value of 0.6 crab as observed by Sweet Bat, which is the highest after the 2006 giant outburst. The giant outburst is also detected by Fermi GBM. The top panel of figure shows the variation of spin frequency during the outburst, and the bottom panel of the figure shows the evolution of pulse flux using Fermi GBM. The NICER pulse profiles show a strong luminosity dependence, which implies that the beam patterns change significantly with luminosity during the outburst. However, the beam pattern can be more complex than a simple pencil or fan beam, and the beaming pattern evolves significantly during the outburst at higher luminosity. The beaming pattern is dominated by a pencil beam pattern. The spin period of the source was found to be 41 seconds during the outburst using NuSTAR observation. The pulse profile show a multiple peak feature from NuSTAR observation as shown in the picture 4. The strong energy dependence of the pulse profile is observed from the NuSTAR observation at low energy. Multiple peaks and dips are prominent and evolve to a broad simple peak at a high energy. The evolution you can see from low energy to high energy. We have estimated the pulse fraction for the energy range for which the energy resolved pulse profile is shown. Figure 5 shows the variation of the pulse profile with energy, which shows a positive correlation of pulse fraction with energy. Recently, another X-ray pulsar 1A0535 also showed the strong energy and luminosity dependence of pulse profile during the giant outburst of 2020. Figure 6 shows the similar kind of pattern which we have found from the 2022 observation. This result is also published in recently published in MNRS. So here also we have seen the similar kind of the luminosity and energy dependency. So we have investigated the CRSF feature using the NuSTAR spectrum. The energy spectrum is shown in the figure 7. It was fitted with a composite model with 2 components, a black body emission and Carter power law. An iron emission line was also found near 6.4 keV. We have not found any signature of the cyclone line from the NuSTAR observation. So here is the conclusion. What we have learned from this giant outburst of this source during the 2021 outburst, EXO 2030 plus 375 exits, the critical luminosity and a state transition from subcritical to supercritical regime took place. High variability of pulse profiles is observed with luminosity. The beaming patterns are evolved significantly with luminosity. The energy spectrum can be described with absorbed Carter power law, and an iron line feature was also found, and no evidence of any CRF feature was found from our observation. So we acknowledge NuSTAR and NICER for the scheduling of TO observation, quick scheduling of the TO observation, and with that I thank the audience. So if there are any questions, you may ask now.
Thank you, Sabyasachi. Any questions? There is one question in chat box. Can you comment on CRSF of this source?
Okay. The CRSF feature of this source was a bit confusing in the sense that from the earlier observation, some of the observer actually found the very weak CRSF, but from the next subsequent papers, the finding of CRSF was nulled. So so it was not quite sure that whether there was any CRSF from this source. So we had only one NuSTAR observation, and from the observation which we studied, we have found no CRSF feature. We studied it very carefully, but we have not found any CRSF feature. But I will say that more observation is required to be more sure about the CRSF properties of this source. But from the observation or from the NuSTAR observation which we studied, that there's no CRSF feature from this source.
Okay. Thank you very much. Thank you. Thanks for the talk. So with this, we are concluding this session. Thank you, everyone.